Okay, good afternoon. Can you guys hear me well on Zoom? Perfect. Thank you, Aiden. We can go ahead and begin. So good afternoon, to all of you guys. The reason I had kind of shifted the modality of today's lecture to fully being on Zoom and fully doing it from home is I've been due to the weather change, I've been ill. I felt very ill for starting yesterday and today. So I'm hoping that next week lectures will be going back to in person and as usual on Zoom. So a few course logistics that we'll speak about before we dive into our lecture is that assignment two. Thank you, Ian. So assignment two is in the process of being graded now. It was due this Sunday. So the grades for that should be done by the end of this week or sometime early next week. I wanted just to update you on that. Assignment three has already been out and we said I have announced it, or I think earlier, sometime last week, and it's going to be due November the 23rd. Okay. Yes, let's check here. Yeah, so assignment three was released on Friday, the 7th, and will be due the 23rd. And remember, you always have 2 days to submit after the due date with a late penalty. So just keep that in mind. And then our final exam, based on the vote that we had, um, it will be on the 24th. So here's how we're looking on for the rest of the modules. So currently, we're in week 13. And Monday lecture was about distance vector, the Bell-Manford algorithm. Most of you guys are aware of this algorithm. I'll do a brief recap of it today before we move into one of the practical routing protocol. You could say OSPF, BGP, or hot potato routing. We will talk about that. Next week, we will have two lectures, still in chapter 5 of the network layer, and we will wrap up chapter 5 next week. And then the following week will be the final exam. So on that Monday, that week will be no class. The exam will be take home, and then Wednesday is Thanksgiving break. And the 16 is going to be, since we're taking them final early, you'll have nothing on that last week. Okay. Uh, yeah, so this last announcement that I made was regarding the lecture on Monday. And this was for today. Okay, perfect. So the lecture on Monday was about the Bell-Manford algorithm. Here's the recording. That's full and detailed explanation for that given lecture. I will do a recap of it today, obviously. And then we have here, I put a simple video step by step to explain the Bell-Manford algorithm. Okay. Do we have any questions? Um, I don't think if you have any questions before we begin our lecture, please let me know. But I think it should be very straightforward. We only have the homework three left and the final exam. And have you guys received any notification to complete the SPIs or any notification once you log into your UCF web course? Not yet. Okay. Um, they sent us an email regarding the SPIs, which is basically an evaluation from the students to the instructors, to the professors that are teaching the course, and it's completely anonymous. So if you have not got notified about it, don't worry about it now. You should receive a notification, or when you log into your UCF main account, you should see that as like a pop-up page. And it has like a bunch of questions. So I would highly appreciate if you guys would fill that out. Just leave any type of feedback that you saw on the class and what you liked, what you didn't like, and that would be highly appreciated for my future academic career. Okay, so let's talk about chapter two very quickly. I'm not gonna spend a lot of time on it. I just want to give you the main idea of it, and I highly suggest that you watch the recording fully again to completely understand it. So this is a roadmap, and last week on Wednesday we talked about link state routing protocol. We gave an introduction to the control plane of the network layer. We talked about link state protocol, and we talked about the Dijkstra algorithm. In this lecture, or Monday lecture, we talked about the distance vector, and distance vector is going to be using the Bellman-Ford algorithm. And basically, the Bellman-Ford algorithm is different from distance vector. So the distance vector, which is the Bellman-Ford algorithm, is different from the link state protocol and different from the Dijkstra algorithm. The Dijkstra algorithm knows the full roadmap of all the routers or all the network. The distance vector using the Bellman-Ford algorithm only knows its neighbors. So it would only know its neighbors, then basically we would wait for, we would find the paths from given node to another node. So here, for example, we have here many routers such as U, V, W, X, and Y. This is the same example that we had with the Dijkstra algorithm, but here we're explaining it using the Bellman-Ford algorithm. Okay, so we want to get from destination U to Z, and we want to know the paths that connect U. So the Bellman-Ford algorithm is going to just list the possible paths. So when we have D here, D stands for distance, and we basically want to find the shortest distance from U, given node U, to node Z. Okay, so the first path we have is so we are trying to find the minimum path. There's going to be basically we have the first path here is going to be CUV, so from U to V, and then given node V to Z. We have another path as well from U to X, and then given X to Z, which is the second path. And then we have U to directly to W, and then given W, we go to Z. So we basically add up all the weights and find the minimum path. Then we take that minimum path and we kind of sent the new distance vectors for every router to all the other nodes, all only to its neighbor nodes. And the neighbor nodes would take that distance vector if the information that is coming is more sufficient, meaning more it achieves a shorter path for us, then it will consider it. If that path is already short in the first place, then it will just discard it. Okay. So basically, the distance vector algorithm, or you can say the Bellman-Ford algorithm, has three main steps, and I emphasized that in the lecture. We have a waiting step, so we are waiting for a change in the local cost. This could be a change in the cost of node U to node V, or a message from the neighbor, meaning from node W or whatever that neighbor is. We would recompute the distance vectors estimates using the distance vector that is received from the neighbor. And then if DV to any destination has changed, we notify the neighbors. So it's kind of like an iterative process. Here's a good analogy that explains the distance vector algorithm. So imagine a group of your friends are sharing restaurant recommendations, and each friend knows the distance or effort to a few restaurants. So when one friend finds a shorter route to a restaurant, like maybe a shortcut, they would tell their friends. And then those friends would update their own nodes or update their own path. And if that shortcut helps them too, they would pass it on to the others. So if nothing changes, no one will say anything. So the group stops sharing. So in this analogy, you can think of the friends as the routers, the restaurants as the destinations, the travel time is the link cost, and sharing updates are the DV updates, the distance vector updates. And silence is convergence. And convergence is the last phase you could think of, or the last states and the iterations, meaning that we have reached the shortest path for the whole network. So the whole network maps the routers that are in place step by step and knows the shortest path within all the given network. So it's kind of like we are exploring a node by node. So once we explore a new path, kind of update our own given distance vector so that we know that shortest path. And it's kind of like diffusion, node spreading in essence. So here we are looking at here just basically a figure, and we have multiple routers. Okay, and with this multiple routers, we can have a few things. We can have a missing link, as we see there's a missing link from C to F, and there can be a larger cost from A to B. By us doing the distance vector algorithm, we can cover paths that are shorter for us. For example, if you wanted to get from B to A, it would cost us 8. But once we discover that E and node D, we can take that shorter path and it would only cost us 3. Okay, so each router is going to have a distance vector. This is going to be basically kind of like a 1 by 1 matrix where we are comparing node A, so distance A, to all the other nodes. And we would put infinity, there's no direct link, or we would put the cost if there's a direct link. So every node would only connect to its neighbor, meaning that A only connects to B and D. So here we see that for the distance from node A to A itself, basically a real loop that is going to be 0. And then from A to B, it's going to be 8. From A to C, since we have no connection, that is going to be infinity. And distance A to D is going to be 1. Okay, so that is at time series 0. Then we move to time series 1. A would send its distance vector to node B and D. And then we would do computation again, find we redo the distance vectors, and then we send the new distance vectors to our neighbors again and again. We would receive distance vectors from our neighbors again. We would also do computation, and then we would send those until we reach the convergence or the last iteration step. Okay. And this is a deeper example that I have explained in the lecture that kind of gives you a more in-depth. We uncover not only the concept of the distance vector, but we also apply um, uh, mathematical step by step to do the computation for 3 given nodes, B, A, and C. Okay, so I'm gonna leave that to the recording. And basically here is just something to highlight the diffusion with distance vector. At each given iteration or time step, we are uncovering or kind of like discovering the whole network. So in time iteration 1, we only discover nodes C and B. And iteration 2, we discover E and A. No, iteration 3, we discover H and D. In the last iteration, we uncover the whole network. So we know the shortest path. This is the convergence steps. Okay. Here we talk about the comparison of link state and a distance vector algorithms, whether it's message complexity, spread of convergence, robustness, and that is for you to read. Here's a good kind of table that compares them side to side. So for message complexity, we know that with link states, it becomes an ON to the power of 2 because messages are exchanged across all routers. Distance vectors is kind of more efficient when it comes to that, meaning that we only exchange information only with our neighbors. So the number of messages depends on the convergence time, the number of iterations we have. Speed of convergence, that is usually faster because routers have full network view, but it may oscillate styling, that is for the link states, because we know the whole map or overview of the given network, okay? In terms of robustness, faults are localized, so a bad link only affects the router own table. And here, distance vectors, we cover some limitations with distance vector where false updates can spread and propagate, which causes kind of black hole. Okay, for computation, we have the Dijkstra algorithm that uses the link state and distance vector that uses the Bell-Manford algorithm. And here are some protocols that we will talk about in today's lecture. So hopefully that gave you a quick overview before we begin our next lecture, but I highly, again, suggest that you watch the Monday lecture, which is under week 13, okay? So let us begin our lecture today. And let me just can you guys see the presentation? Just to confirm. And you can hear me all well, right? Okay, thank you, Alan. Okay, perfect. So as usual, the lecture is recorded and some of the slides are borrowed from the book. So last lecture, we talked about distance vector, but we stopped at intro ISP routing, which is the OSPF. So if you watch the last lecture from Monday, you will see that our stopping point is exactly here. So this is where we are picking up for today's lecture, okay? And basically, we're going to discuss OSPF, which is basically standing for Open Shortest First Path, or Open Shortest Path First. And this is going to be a link state protocol that used with a single autonomous system, and it helps routers build a complete view of the network topology and compute the shortest path to each network destination. And this uses the Dijkstra algorithm. Okay, so it is widely used because it supports hierarchical design areas, fast convergence, and scalability. Okay, so now that we have seen how routing works or simpler networks, let's talk about what happens when we try to apply these ideas to the entire network. So far we've been studying routing in idealized settings. So we assume all routers are identical and the network is flat, meaning every router knows about every other router directly. But when it comes to the real world internet or in practice, this is not how the internet is. Okay. So the first thing that we have is scale. So we know that the internet includes billions of destinations. So a single router can't store every destination in its routing table. Okay. So constantly exchanging huge routing tables would overload the links and make the network inefficient. So we need to find a path kind of that deals with the scalability. This is why we need hierarchical routing structure to manage scale. The second thing we have is an administrative autonomy, as the internet isn't one big unified network. It's a network of networks. So each organization or ISP runs its own part. This is going to be called an autonomous system, and also the acronym stands for AS. So each AS obviously is going to have policies. It's going to want to have its own control for routing, and it wants to and how it connects to others. So the autonomy we have here introduces boundaries between internal, which is going to be intra AES, and external inter AS, and we will talk about the difference between them here. So we just saw that routing faces two main problems. The first one is scalability and administrative autonomy. So the solution to those is going to be to organize into manageable regions. This is going to be called autonomous systems. Okay, so that internet would group routers into logical regions. This is known as the AS, autonomous systems, or also called as domains. So each AS is typically managed by a single organization, such as an ISP, university, or a large company. So for example, here at UCF, the UCF would have an AS and they are managing their own AS, okay? So the structure is going to help limit the complexity that we have by containing it with smaller controlled regions. So we have intra AS, aka intra-domain, and this handles traffic within the within the AS. So all routers in the AS must see and use the same routing protocol internally. So for examples, we can use OSPF or RIP, and routers in different ASs, which is different internal protocols, which allows flexibility for each organization. So it's kind of similar to the idea of subnetting. We are subnetting kind of devices here, but subnetting devices when it comes to network subnetting, but here we are subnetting the actual routers, okay? And each AS can have its own routing algorithm, and it must use that routing algorithm internally. We're obviously going to have a gateway router that's going to act from the internal to external traffic, and that is going to sit at the edge of the AS that connects to routers and other S's that we have. Then we have inter-AS, aka interdomain, and this manages communication between the S's. So, for example, if UCF and USF have two different S's, we would use inter-AS for those two to communicate with each other. Okay, So gateway perform inter domain routing, so allowing traffic to move from uh, between networks that use different internal routing schemes. So this is a type of routing that defines how data leaves on one network and enters another, um, ensuring a global connectivity between the internet. Okay. Here is a very cool thing that I have messed with, and you guys can mess with as well. It's basically called hackertarget.com, and you can do an IP lookup, and you can check, or you can kind of explore information about the AS. So it tells you which IP belongs to which AS and how they are connected. And I actually have done that here. So if you visit the website and you can mess with this in your own time, I have pinged ucf.edu, and that allowed me to get the UCF IP address. We here see we have all ping requests are timed out, and this is something that is typical and normal, meaning that the DNS server for UCF is blocking these echo requests, maybe for security reasons, or it could be for any reasons. Okay. So if you check that, if you click on that website on your own time, or maybe you can do now if you like, this website is going to take you to something that looks like this. So autonomous system lookup, AS, ASN, and IP. So basically, I entered the IP address of ucf.edu, and it's going to show us details. So the details it shows, we can see the IP address belongs to AS8075, and this is going to be a Microsoft, um, kind of a Microsoft hosting network. That means traffic to UCF EDU is actually being served through the Microsoft hosting network, most likely through Azure or Microsoft CDN's infrastructure. Okay, so this kind of shows you how routing connects globally. Even universities' websites may be routed through a large external AS for performance and reliability. So this simple lookup, and I think there's other tools that do the same thing, kind of helps identify ownership and boundaries between networks. Okay. So now we know that the network or maybe the internet can be broken or segmented by autonomous systems, and those autonomous systems operate individually. Here we see three different autonomous systems: AS1, AS2, and AS3. So each one of those regions, the ones in blue, um, uh, represents a separate network under its own administrative control. And those routers inside each AS communicate internally, while some edge routers connect to other routers. So these boundaries are going to play a key role when we discuss how routing information is between the S's here. So inside each AS that we have, routers use intra AS routing protocols like OSPF or RIP. We will talk about more of these in detail. That is going to be to exchange information and find paths within the same AS. And basically, all the ideas, this is why I highly suggest to watch the last lecture and the one before, is because everything that we discuss when it comes to these protocols are built either on link state protocol, like the Dijkstra algorithm, or the Bell-Manford algorithm that uses distance vector. Okay, so now when the communication happens with intra-AS routing, it can use link states or distance vector. Okay. Then we have inter-AS routing, and this is going to be external communication between the S's. So we're going to use a broader gateway protocol, BGP, which is going to come into play, and we will talk about that more in detail. So this will handle the communication between the S's. So maybe this can be UCF here, this can be Stanford, this can be Massachusetts, so different universities that have full control over their kind of domain. Okay. We have the forwarding table, and this represents how routers store the decisions. So every router is going to maintain a forwarding table that tells it where to send the packets next, based on intra-AS or inter-AS routing inputs. So it's kind of like the navigation chart that is built and used internally and externally. Okay. So we have the intra AS routing determines entries for a destination within the same AS as we said, and these intra AS can use algorithms like Dijkstra or Bellman. So, for example, AS1 here we have, or like within AS1, router 1A knows how to reach router 1B, 1C, and 1D. Okay, so that is the intra, which is basically think of internally. Inter AS is going to be externally. So this is for external communication or external destination routing. So routers here in AS1 want to contact AS2, so they would use the edge routers, which is 1B, that would connect to A. But we have that given link uses a specific protocol for that. Okay. Here's a human analogy to kind of clarify intra-AS versus inter-AS routing. So intra-AS is going to be like driving in your neighborhood, and everyone is going to follow the same local rules. So they're meaning they are following the same protocol, and you know all the nearby roads and shortcuts to get around efficiently. Inter-AS routing is like traveling between maybe cities or states. So each state is going to have its own traffic law and routes. That is going to be the different ASs that we have. Then you rely on highways, which is going to be the BGP protocol to move between them. So you don't care how the city manages its own roads, you just need to know how to get there. Okay, so here we have an example. So suppose router AS1 here is receiving a datagram to go to a destination outside AS1. So AS1 here is receiving a packet, and this packet is destined to go to somewhere or to another autonomous segment or group, you can say. So it needs to figure out how to send the packet to the correct gateway router so that connects to another AS. Okay, so the first thing that we have is going to be basically the router must decide which gateway router in the AS1 should handle this packet. So notice why there is a question mark given here that represents the router dilemma. So there could be multiple gateways in AS1. Each could lead to different neighboring, like AS2s or AS3s. So then the router needs to determine the best exit points based on the inter-AS routing information. So this is where inter-domain routing is going to help internal routers make smarter forwarding decisions. So they kind of work hand to hand. So when we have a packet that is going from one domain to another domain, internally is going to help us find the shortest path, the best path, and externally is going to deliver that packet for this. Okay. How AS1 learns reachability. So for this to work, AS1 inter-domain routing must learn which destinations are reachable through the neighbor AS. For example, traffic to come to some destination may need to go through AS2, but others might need to go to AS3. So then AS1 here must propagate the reachability information to all routers within AS1 because we are not sure if it needs to reach AS2 or AS3. So internally, we need to have kind of an overview of the whole routers in that domain. So that coordination is going to be important and ensures consistency across the AS and efficient packet forwarding towards the internet. Here, we see most common intra-AS routing protocols that are used within networks today. And these are going to be used and responsible for internal communication between routers in the same AS. Okay, so first thing that we have is we have RIP. This is kind of one of the earliest routing protocols that is defined in RFC 1723. And it uses distance vector approach where routers exchange routing tables every 30 seconds. So it is simple and easy to configure, but it has major limitations like slow convergence and poor scalability. So RIP is kind of like no longer widely used in modern networks, but it remains one of the small, kind of useful for educational steps. We have EIGRP, which is Enhanced Interior Gateway routing protocol, and this is going to be a Cisco development with enhancements for faster convergence and reduce overhead. So it uses a combination of link states and distance vector. So kind of often called as a hybrid protocol. So it became an open standard in 2013 in RFC 7868, and now it is used by many enterprises in Cisco dominant environments. And then we have OSPF, which is open shortest path first, defined in RFC 2328, and that is using link state routing protocol with SS today. So unlike RIP or EIGRP, OSPF builds a complete map of the network and uses the Dijkstra algorithm to compute the shortest paths. And it also supports hierarchical design areas to improve scalability for larger networks. And there's also a similar ISO standard called ISIS, which functions almost the same as OSPF. So we'll dive into OSPF more in detail. And now that we know OSPF is one of the main intra-AS routing, internal routing for a given autonomous systems, we want to know how they actually work and why it became the standard choice for large complex networks. So the first thing that we have to clarify is the word open means the protocol is publicly available and not vendor proprietary, like unlike older ones such as EIGRP. Okay. So OSPF is going to be a link state routing protocol, meaning the router maintains a complete map of the network topology, similar to the Dijkstra algorithm. Okay. And each router is going to receive updates from the others and build the same network view. So anything that we discussed in link state protocol or Dijkstra algorithm, the OSPF implements. That's why understanding those two protocols and those two algorithms are going to be very important moving forward. Okay. For security, that is one important aspect of the OSPF is that all the messages are authenticated to prevent malicious routers from injecting false routing information. So all the messages are going to be authenticated, and this is going to help against attacks like route poisoning or topology manipulation. And all authentications can be configured using maybe password-based authentication or cryptographic methods, depending on the version and obviously the network policy. So here, what we have is that we discussed OSPF, and let's see how OSPF is designed to scale efficiency for large networks by using a hierarchical structure. So keep in mind that OSPF uses a two-level hierarchy to organize networks. So we have the backbone, which you can think of area 0, and we have the local areas. So this is where each group routers and networks are segmented into manageable segments. So that reduces the link state of the databases. Okay. And we have LSAs, which is link state advertisements, are flooded only within an area or within the backbone, not across the entire SS. So we will discuss how a routing kind of like advertises its routes, and this is going to be something that is important. So routers only know how to reach area, in each an area, not in their full internal structure. So in the diagram, you can see multiple areas here, area 1, 2, and 3. They're all connected through the backbone. So here we have area 1, area broader routes. So the router here is connecting to an area, the backbone called area border router. Okay, these are going to be the routers that are set at maybe the end, you can say, or the gateway that connects to the backbone. Okay, and we have local routers, and these are going to be operate entirely with a single area, so it doesn't reach the external or have any contact with the backbone. So they only flood LSAs only in their own area and compute using routing state, link state databases, and forward only an external package to the nearest ABR. area border routers. So if if one of those local routers needs to reach out to backbone node, internally connect or communicate with that area border routers that are set in place. Okay. We have the backbone, the boundary router, and this is going to be called as the AS boundary router or maybe ASBRs that connects to the OSPF network or to other autonomous systems using inter-AS routing like BGP. And we have the backbone routers, and these are going to be that run OSPF only with the backbone area and that maintains connectivity with all other areas. So hierarchical OSPF allows networks to grow without overwhelming the routers with unnecessary information. So next we'll look at how OSPF actually changes information and how this hierarchy improves scalability. So we move to routing among ISPs by using BGP for external routing. So we move on to the Broadway border gateway protocol comes in, and that is going to handle, as we said, external communication that is happening between the autonomous systems. So that makes the protocol essentially powers how it powers the global internet. Okay, so BGP or Border Gateway Protocol is going to be the de facto interdomain routing protocol that is used across the internet, and you can de facto is like the glue that holds the internet together. Okay, and allows different networks or different autonomous systems to exchange reachability information with another one. So each AS uses BGP to announce IP prefixes, its own and how other S's can reach them. So in other words, if UCF has an AS and USF has an AS, those ASs use the BGP to announce their presence, saying here, these are the networks I can reach and this is how you can get to them. Okay. So BGP provides works between and within S's, so provides mechanism for external and internal communication. We have eBGP, and this is going to be used externally. That is obtaining the reachability information from the neighbor S's. And an example of that is an ISP learning routes from another ISP. Okay, and we have IBGP. This is going to be used internally. This is going to be used to distribute that information within the same AS, within their local routers. Okay, so together the EGP, eBGP, and IGP would be used to learn about the local routers and advertise routes across the network. Okay, and then one important thing is that beyond just sharing the routes, BGP only enforces policy decisions when selecting which routes to use or advertise. So policies are going to be based on maybe business relationships, performance, or security preference. So for example, to give you an idea, is that a policy can be implemented where an ISP might prefer to route traffic through a customer who pays rather than a peer with no payment. Okay, so BGP is not just used to find the shortest path, but it's also trying to find the most preferred path according to network policies. So kind of like the policy comes first as an initial check. Okay. So now we understand BGP computationally. Let's look at how it actually operates between and within autonomous systems. So the diagram here is showing EGP connectivity, and this is going to be connection with external autonomous systems. And then we have the logical IBGP connectivity. This is internal communication. Okay. And this represents the internal communication with these drivers. Okay. We have the gateway routers, and these are the ones that are circled here. So we have 1C, 2A, 2C, and I believe that is 3A. Yes, I couldn't see it with the animation. So 3A, these are all the gateway routers. They're going to sit kind of like at the border of their assets and run both EGP and IGB protocols. So the role is to run EGP with the neighbors um, to learn external routes and distribute those routes internally using IBGB so other routers in the AS can reach external destinations. So this combination ensures that internal and external routing knowledge flows smoothly into each autonomous system, maintaining consistency and complete connectivity across the internet. Okay, so a BGP session is going to occur when two BGP routers known as peers establish a semi-permanent TCP connection, because we said that the messages within BGP is authenticated and encrypted. So there's this using TCP allows them to exchange messages reliably. So through these message, each router is gonna advertise path to different networks prefixes. And BGP is known as a path vector protocol because it advertises not just the destination, but also the entire path the sequence of S's need to reach it. So in the diagram here, we have AS1, AS2, and AS3, and they are ready to exchange routing information using this peering relationship. So let's see how this works. So let's take an example between, you can neglect AS1 here, focus on AS3 and 2. So the gateway router here in 3A and AS3 is advertising a path to X because an X router has joined this autonomous system, and before X was not there. So when X joins in, we need to know how we can reach that X. So we basically are advertising that path to it. So AS3 is telling, hey, it's contacting 2C because this is the border gateway router. And it just basically tells it, hey, if you ever need to reach network X, you can send traffic through me. This is called BGP advertisement. So this is how one AS can inform another AS about the destination reachability. So when AS advertises that path, it makes an implicit process, or promise to AS2. The promise is to forward any datagram sent towards X correctly. So if 2C wants to send to X, it would have to send it to 3A, and 3A is gonna use, as we said, the IBGP for internal routing. Okay, it's gonna find the shortest path to get to X. So we just seen how routers exchange path information between autonomous systems. So now let's explore what happens when policies takes effect, because we know that BGP allows internal and external communication, but also implies these policies. So first thing that we need to know is that BGP advertisements consist of two parts: a prefix, which is going to be the destination being advertised, and a set of attributes. Okay, so these attributes provide detailed information about how to reach that network. And there's going to be many attributes, but essentially there are two important ones. We have the AS path. This is the list of autonomous systems that the route advertisement has passed through. So this helps detect loops and allows routers to choose smarter, more efficient paths. And we have next hop. This ensures each AS knows the next immediate step in the path. Okay. So these attributes that we have, AS path and next hop, make BGP a path vector protocol. So each router, giving each router enough information to make independent policy-based routing. So next, let's talk about policy-based routing. So the decisions within the routing are also policy-driven. So a gateway router uses kind of like an import policy. Here we have, And this is where we decide to accept or reject, kind of like the access control list that we talked about, kind of the rules to accept incoming packets. So for example, an AS might refuse to route traffic through a specific neighbor due to cost, security, or business agreements. So let's take a look at this, okay? Now we take a look at BGP path advertisement with policy advertisement and how policy advertisement affects those path advertisements. So here we have three autonomous systems again, AS1, AS2, and AS3. And inside AS3, router 3A is connected to 3 is going to be connected to 3B, 3C, 3D, and AS3 itself knows how to reach destination X. Okay. So the goal here is that to show how route X is gradually shared outward through BGP advertisements. Okay. So from AS3 to AS2 advertisements, the process always begins with the autonomous system that is doing the advertisement. So that is going to be AS3. So it uses router 3A to send a BGP advertisement to 2C using eBGP. So the advertisement says, hey, I can reach network X through AS3 using router 3A. Okay. So when AS2 receives the update, it checks the import policy to decide whether to accept that path. So assuming the policy allows it, router 2C here would accept the route and share it internally with its own local routers, okay? And then once the route has spread to AS2 here, as we see, it will advertise it to AS1, to router 1C, using eGP again. So now the advertisement now includes the updated path. You have AS2, AS3, and X, okay? So it shows how each AS pretends its own number to the AS path before advertising its route. So now we know how to get to router X through these routes, okay? So now we are assuming the policies that are set are being accepted, but let's see once they're not. Okay, so we here have router 3A and AS3 is advertising the path to AS3X. So it's advertising the path of X. And we know that router X or path X is AS3. And it's advertising it both to AS2 and AS1 as well. Okay. So as a result, AS1 here, gateway routers 1C may receive two different paths to reach the destination X. It can reach it through 3A or 2A, or reach it through AS2 or AS3. So this shows that AS1 have multiple routes to the same network prefix, and they can evaluate and choose between them. So in this given example, AS1 router 1C learns two routes to X here. Okay, so the first path we have is through AS2, and then we go to AS3, and then we go to X. And the other path is a direct contact between 1C and 3A. So we have two different paths. So both paths are valid, but they differ in path lengths, obviously, and possibly policy enforcements. So BGP does not say, hey, let me pick the shortest path. What it will do is it will rely on the policy rules defined by each AS. So let's check the policy for this given. So based on the policy, based on AS1 routing policy, router 1C chooses the preferred path, in this case, AS3 to X, okay? This choice is not really identified in the slide, but it could be a business relationship. It could be shorter paths or longer paths. It could be local preference settings by network administrator. So after we select that preferred route, AS1 1C router would advertise the chosen path to AS3 using AS3 and getting 2x. So hopefully that makes sense so far. Try to break it down as easy as possible. Um, so now we've seen how BGP exchange routes advertisement internally and externally with also policies. And the way of exchangement is obviously going to be by messages. So it's going to be through a set of standard BGP message types. Okay. So BGP routers or peers communicate use TCP connections, and I think that is typically over port 179. It uses TCP for reliability and make sure that the messages are delivered in order and without loss. So you see that TCP protocol not only is used by sending packets, sending processes, but also used for routing messages as well. So that is something to always note. And the message types that we have within BGP is that we have open, and this is establishing a new BGP session with peer and performs authentication. We have update, and this is going to be basically the most important message type used to advertise new routes or withdraw old ones. Keep alive is going to be sent periodically to ensure the connection remains active and no acknowledge open message to acknowledge open messages. A notification is going to just basically report any errors in the previous messages and also use to close the connections. So these messages are going to keep um, maintains the state and synchronization between BGP sessions, or you can say routers. So let's continue on the path advertisement. Here we have inside AS1, router 1C learned the path to destination X is directly to AS3. And also it shared that path with its local routers. Okay, so you can see those three arrows here being sent within AS1 internally. So that means all these internal routers, if they wanted to reach X, they would send their routes to 1C, and 1C has two paths, but we agreed that it would use direct link communication with AS3 using router 3A. Okay. So if we zoom in on AS1, we know how OSPF works with information. Um, so each router inside AS1 already runs OSPF and provides knowledge of the internal network topology. So routers like 1A, 1D know their local interfaces and the shortest internal path to reach 1C. So when OSPF works internally and BGP work together, OSPF is going to handle intra-domain forwarding and BGP handles the inter-domain reachability. So we have two different protocols that are working together. So here we have the forwarding table for router 1D. You can see here the routing table for router 1D, and now reflects this coordination. Okay, so to reach 1C, we obviously use link interface 1. Okay, that is determined by the OSPF for internal communication. Okay, and since BGP says relies on SPF internally to forward the packets inside the next hub, inside the AS for the next hub. So we at 1D to get to X, we use interface 1. So if we are at D, we use to get to X, we use interface 1. Okay, so essentially router 1D knows the both routes 1C, and X uses the next hop interface. So this is kind of like the cooperation between BGP for external and OSPF for internal forwarding. Kind of like you can think of OSPF is like a layer 2 switch for internal forwarding, and BGP is like a router for external routes. Just trying to deliver the idea for you. So previously we saw 1D, how it uses OSPF routing to reach router 1C, and then 1C serves as the gateway destination to X. So inside AS1, all routers like 1A, 1B, and 1D learned through I, BGP, from 1C to the path destination X goes through router 1C. So each internal router uses OSPF to find the shortest path internal route to reach 1C. So for example, at 1D, OSPF says to reach 1C using link interface 2. Okay. And at 1A here, OSPF says to reach 1C use interface 2. Okay. So the router is going to rely on the OSPF to know how to reach the BGP next hop. So for us to reach X, we have to use interface 2. So when router 1A needs to send packets to destination X, it already knows from the BGP that X is reachable through 1C. We know that for sure, for that's external communication, but we also need to know it internally, so we also mark it internally. So destination 1C, we use interface 2, and destination X, we also use interface 2, okay? So we want to discuss why we need separate types of routing protocols instead of one unified approach, okay? And the first major reason is going to be policy. This is going to be called the inter-AS routing. So every autonomous system, like an ISP or organization, wants control over how traffic is routed and how is allowed to send traffic on the network. Okay. In contracts, intra-AS routing happens inside a single administrative domain. Since there is no authority managing it, policy conflicts are going to be minimal. So internal policy are going to be minimal for local. So performance and efficiency takes priority, but for external routing, policies needs to be implemented. For scale, scale is that the internet has thousands of autonomous systems and millions of routes. So the inter-AS routing needs to handle this huge size efficiently, which is why we use hierarchical designs. And this approach reduces the routing table size and limits the frequency of updating, making global internet more scalable. We also have performance. So inside AS, routing protocol like OSPF can just be tailored and focused for speed and optimal path selection. But in enter AS routing, we can policy takes precedence over performance. So BGP might select a longer path if it aligns with the business or security rules. So while the AS is routing optimized for efficiency, inter-A routing prioritizes control and stability across organizational boundaries. So now that we have compared intra and inter-AS routing, let's look at a specific BGP routing. And this is kind of like a routing behavior that is inside BGP called hot potato routing, which shows how interdomain routing can influence interdomain decisions. It is very simple. So here, just like initially we have different autonomous systems, AS1, 2, and 3. And AS2 here is going to have multiple routers. We have 2B, we have 2A, we have 2C or 2D, and there's link weights that is going to be shown on the diagram. So to get from 2B to 2C, the link cost is going to be 112. So routers in AS2 will learn through IPGP that there's two possible paths or to exit points towards AS3. If we want to get to AS3, there's going to be two possible paths for us. One through 2A. So 2A goes to 1C and then goes to 3A. And then we have a one path that goes from basically from 2C directly to 3A and get to X will get to AS3. So the question with hot potato routing is which gateway will router 2D choose? Will it choose 2C to get to AS3 or chooses 2A to get to AS1? So that is the idea. So router here. So router 2D, which is highlighted, learns via IBGP that it can reach destination X through either 2C or 2A. So both routes are going to lead to X, but each one has a different cost. So the path to 2A is going to be 201, and the path to C is going to be 263. Okay, so even though both paths leads to X, OSPF considers the internal link cost before thinking about the external paths that we have. So hot potato routing is gonna say that each router chooses the nearest exit point based on the lowest inter-domain cost. So router 2D chooses to send packets via 2A because that path has the lowest cost, 201. So always it chooses the lowest cost. So that means 2D um, uh, chooses to send packets to 2A because that's the path that has the lowest cost. And notice that ignores the inter-domain cost or the number of AS hops. We know that the number of hops is shorter here, so it does not really care about the number of hops. It just cares about the cost. We know that there's a shorter path but higher cost here, but it always takes the lower cost here. Okay. Lastly, we need to talk about achieving policy via advertisements, and we know that policy advertisements are implemented. Okay, so we want to see how ISPs apply routing policy to control traffic and avoid carrying transmit traffic for others. So in this example, we have ISPs with three routers. So ISPs are going to be the provider networks. Those are the big orange boxes. And this is going to be basically A, B, and C. W, X, and Y is going to be representing the customer's network. Okay. So the provider network is the larger shape that would connect these customer networks. And the key idea is that ISP only wants to route traffic for its own customers, so not between other ISPs that we have. So this is going to be a real common real world policy. So ISPs want to avoid being used as a middleman. So let's say we have different provider networks, and here we have AT&T, Spectrum, and maybe um, um, AT&T, Spectrum. Maybe we can have another one here. Maybe you could say T-Mobile, Verizon, if they do have one as an ISP, is that, and for example, T-Mobile does not want to be used, or Spectrum does not want to be used here as a middleman to deliver that traffic. Okay, so router A here, you could say, or maybe say A here advertises its AW to both B and C. Okay, so A advertises connections to both AW to B and C as we see here. So that means B and C now, the traffic is destined for W can be reached through A. Okay, so these advertisements also help the ISP's internal routing maintains reachability within the same network. Okay, so B, router B is gonna apply policy decisions. It does not want to advertise the path to B, A, W to C. Okay. So because none of C, A, or W are B's customers. Okay. So if B were to advertise the path, it might end up carrying transit traffic from C to W. Okay. So B filters the advertisements, meaning C never learns about the C B A path. Okay. And we have here, since C here never receives B to A, it only knows the path from CAW. So CAW, it cannot use B because the policy that is set by B. So as a result, C would route directly through A to reach W, bypassing B entirely. So this enforces ISP business policies to route to and from its customers, not through other provider networks. We could have X, and here X is highlighted and is a dual homed customer, X and its policy. Now customer X is connected to both providers B and C. So that makes it a dual home customer. And dual home customers often want redundancy, meaning if one link fails from X to B, they can use X to C. However, X does not want to become the transit between B and C. So as a customer, you want to become the transit between B and C as provider networks. Okay. So X will not advertise any routes learned from C to B and vice versa, or from B to C. So this way, X is going to stay connected to both providers for its own use, but never becomes a middle path between them. Okay. So this is an example that highlights how BGP advertisements directly reflect business agreements and routing policies. So each network or each customer um, has alignments, policy alignments, maintaining both efficiency and profit control. Okay. We have two more slides. So BGP route selection is we want to look at how the router actually decides which route to use when multiple options are available. So in practice, a router may receive multiple routing advertisements for the same destination or autonomous system. But BGP must use one path to use for the forwarding table. Okay. So the decision process follows a specific order of criteria. You have local preference. It's going to be policy based on policy decision. This is the most important factor, and these are highlighted from kind of like the highest decisions that we must follow. So that an administrator assigns a local preference value to control routing based on policy. Okay. Shortest AS pass is going to be if local preferences are the same, BGP will choose the path with the fewest AS hops. Okay, this will help reduce the number of network packets must traverse. Next hop router, hot potato router, is that if the AS path links are equal, BGP selects the path with the closest next hop router based on the internal network costs. So this is the hot potato principle, get the packets out of the network as quickly as possible. Additional criteria is if the above factors tie, BGP might use tiebreakers such as router ID, origin type, or route age. And that is all for today's lecture. So we discussed OSPF and BGP, and we see how OSPF works internally and BGP works externally, and how BGP not only routes internally and externally, or local and not local, but also applies policy that are set by the ISPs or by the customers. Okay, so this is it for today's lecture. I will see you all next week as we move on to our next topic, which is going to be software-defined control plane. Okay. Do we have any questions? If you have any question, guys, I can answer them now. But if you do not, then I will see you next week, next Monday. See you. See you later, Ian. Thank you.